Okay, the next test that we are going to learn is the comparison test. This is also, you can consider it as a theorem as well. And this comparison test and the comparison test that we did for integrals is almost the same. So the basic idea is, if you have this sort of a comparison, and if the larger series, see, if this larger series converges, then the smaller series will also converges. And if the smaller series diverges, see, now here in this second statement, the smaller series is represented as Bn, and if the smaller series diverges, then the larger series will also diverges, right? Now you don't have to like by heart all these things, but just get that natural feeling about this, right? Because if the the fundamental idea that you should have when you say a series converges is that it goes to a finite value, right? So if the smaller guy blows up, it's like if it goes to infinity, that is a very large value, then you cannot have a finite value for the the larger one, because even if the smaller person goes to infinity, then this larger guy must go to infinity. And in the other way, if the larger series goes to a finite value, and due to this inequality, the smaller one should be enclosed by the larger one. So if this larger one is finite, then this smaller one cannot blow up, right? Okay, and there's one more thing. Now all these terms that we are doing the comparison should be positive. Okay, now if you can't do the comparison for series like this, okay, because here you will have both negative and positive terms, but if you are using the comparison test, then both an and bn should be positive, right? Let's do some examples. Let's determine the convergence of this series. Let's see whether this series converges or diverges. So for this one, let's take the general term an of the given series. So we can see now, these are some techniques that you should be familiar with, right? So now here the idea that we are going to use is, if we have a fraction and if the denominator is reduced, then the total value will increase, okay? And you should see that all these terms in this denominator are positive. So if we consider this denominator, since all these values are positive, if we eliminate two of these positive numbers, then the remaining denominator or the remaining value will be less than the original value, right? So that means 2n squared plus 4n plus 3 will be greater than 2n squared, okay? So you can do all that only if you have a positive number, right? Say if we have like negative numbers, 2n squared minus 3, you can't do this one, okay? Without, like, you cannot just get rid of a negative term and write this same inequality, okay? You have to be careful when handling with these numbers, right? So now, but here we don't have any problem with that, because all these terms are positive. And so when these two terms are removed, the remaining will be less than the given denominator. So we will have, and when you take the consider the whole fraction, we will have this inequality, right? Because this is greater than this one. So we can consider this as our an and this as our bn, right? And you can see that the sequence bn can be written as 5 over 2n squared, and here you can write 5 over 2 1 I will write it properly, 5 over 2 sigma 1 over n squared. Okay, so from now here, see, now in this case I took 5 over 2 out from the sigma notation, right? But remember, now when you have only a constant term, if you have only this one, now this has nothing to do with the comparison test, but anyway I should mention this one as well. Like if you have just a constant with the sigma notation, then you cannot just take the 5 over 2 out and like just forget about the sigma notation and write the answer as 5 over 2. Okay, so this means you have a sequence of 5 over 2 terms added together, right? And here what happens is it was something like this, right? 5 over 2 an sigma, right? That means you have a sequence of 5 over 2 a1 plus 5 over 2 a2 plus 5 over 2 a3. Likewise, these terms are added together. So these terms added together will give you the same idea that like a1, the sequence an added together and multiplied with 5 over 2, right? So don't get these things mixed up, right? Okay, so that's something not related to the comparison test. Now anyway, we can write the series bn as this one, and you can see like now we have already discussed the convergence of this type of a series, right, called the p test, and here p is greater than 1, so this series will converge. That means the larger series will converge, therefore the smaller series will definitely converge. So as the answer you should write from the comparison test the original series converges. Okay, because now if you are writing the answer in a correct way, first you should say since p greater than 1, like, okay, or else you can even mention since 2 is greater than 1, sigma 1 over n2 converges, right? Therefore from the comparison test this series will converge. Now let's consider this series. We also discussed the same series under integral test, right? But we can also use the comparison test to determine the convergence of this series. Now when I say determining the convergence, it can either be considered as the as a converging series or a divergent series, right? Okay, so when it comes to this one, what you have is like we might not be able to compare this series with anyone if we start our indexing from 1. Okay, now we are going to compare it with this series, right? So basically what we need is a comparison between this one and this one. Okay, now you can see that both terms have a same denominator, so it's just a matter of comparing these two, right? And just by looking at the ln curve we can see that now I explained the same thing in the previous video under integral test also, and I recommend you to go through that as well, right? We saw that at E, the ln function value, now here since it is mentioned in K, I will indicate it with K. At E, the value is 1, right? And E is equal to 2 point something. So starting from 3 onwards, value of K will be greater than or equal to 1. Okay, so ln K will be greater than 1 for all K values greater than or equal to 3, right? Not for values 2 and 1. And you can divide it by the same number. So that means if we consider this as BK and this as AK, right? We have a comparison between the two terms, but starting from K greater than or equal to 3, right? So we have AK greater than or equal to BK for K greater than or equal to 3, right? So it's like we are comparing these two series, right? Instead of starting at 1, we start both our series from 3, right? And we know from the P-series test that the smaller series diverges because P is equal to 1 in this case, right? And from the comparison test, we can say that this series will converge, but originally you had K equals 1. And remember I mentioned adding or combining finite terms to a series will not make any difference to the convergence or the divergence property. So if we know that this series converge, then definitely this series will also converge, right? Okay, and there are two more things that I want to highlight when it comes to the comparison test. One thing is that here we are comparing term by term. Okay, so if we have two series like this, we are like, and if we list down the terms like this, A1, A2, A3, A4, A5, and likewise, and for B1, B2, B3, and likewise, we are comparing these corresponding terms only. Okay, A1 with B1, A2 with B2, but we are not going to compare A2 with any other term in the sequence Bn. Okay, we are just comparing like the similar terms only. What I mean by the similar terms is the ones with the same indexing. Okay, so we compare An with Bn only, right? So we only need this relationship for the comparison test. And the other thing is, for this comparison test, it doesn't work the other way, right? So if the smaller guy diverges, that means now this is the smaller series and it is enclosed in the larger one according to this relationship. So if the smaller guy explodes, then the larger one should also explode. But that means if the smaller one diverges, the larger one should also diverge. But if the smaller one converges, right, if this smaller guy does not explode, we cannot predict anything about the larger one, right? It may or may not converge, right? And the same thing applies the other way. If the larger guy diverges, right, we cannot say anything about the smaller guy. It can also diverge or sometimes it can converge. But if the larger guy converges, that means if it does not explode, then definitely the smaller guy should converge. It cannot explode because it is enclosed in the larger one, right? Okay, and in the next video we will go over a different test, where test in the sense a theorem.